Modern astrobiology has reached a point where signal collection is constant. The bottleneck is the sheer volume of data we have to filter. Breakthrough Listen generates as much data in 24 hours as previous SETI projects managed in an entire year. Processing this requires navigating archives that scale into the petabytes. The primary challenge for the Green Bank telescope is the exponential growth of our own radio frequency interference, or RFI. GPS satellites, mobile phone networks, and defense radar systems are currently filling the radio spectrum with a density of terrestrial noise that masks potential external signals. Legacy know-what algorithms utilize rigid, hand-coded thresholds. These are optimized for narrowband, continuous signals with a steady Doppler drift, the specific type of transmission researchers originally expected to find. These classical models fail to recognize signals that are complex, modulated, or transient. If an event doesn't fit the pre-programmed criteria, the algorithm ignores it. The search for extraterrestrial intelligence now relies on unsupervised anomaly detection, identifying mathematical patterns that simply do not belong in the background noise. This requires a shift toward know-how models. These are feature-learning neural networks designed to learn the characteristics of the data itself, rather than following a list of instructions. This comparison shows the technical difference between classical thresholds and a deep learning architecture called beta VAE. Classical thresholds suffer from high false positive rates. Because processing speed scales linearly with the amount of data, they eventually create more candidate signals than researchers can manually verify. The beta VAE approach uses dynamic feature extraction to build RFI resilience. It learns the specific patterns of human-made noise and isolates them from the raw signal. Deep learning allows us to search past the specific signal shapes humans once hypothesized. It isolates mathematical deviations directly, removing the bias of what we expected an alien signal to look like. Peter Ma applied a beta convolutional variational autoencoder to legacy data from the Green Bank telescope. The model was trained by blending real observational data with simulated technosignatures, teaching the network to recognize the subtle markers of an artificial source. Raw data is condensed into a latent space representation, allowing the network to identify non-zero Doppler drift. This uncovered 8 highly probable, previously undetected candidate signals. Measuring only a few hertz, they were completely hidden beneath spikes of terrestrial interference during previous sweeps. These results prove deep learning isolates verifiable physical anomalies that hand-coded algorithms are unable to see. This logic also applies to optical data. NASA uses the ExoMiner deep learning framework to validate light curve transits captured by the Kepler and TESS missions. ExoMiner separates genuine exoplanets from false positives like eclipsing binaries, ensuring that researchers focus on the most viable planetary candidates. However, managing deep space assets from Earth faces a physical constraint: light speed latency. We cannot rely on real-time human control for sensors millions of miles away. The solution is edge autonomy. The Perseverance rover on Mars already uses AI to conduct science without waiting for instructions. The PIXL instrument on Perseverance uses AI for real-time X-ray targeting. If it identifies minerals like phosphates or carbonates, it can autonomously trigger high-fidelity scans before the rover moves to its next waypoint. This is critical for the Europa Clipper mission. Dealing with high radiation and limited downlink speeds, the spacecraft will use onboard AI to triage data, deciding which scientific measurements are important enough to send back to Earth. AI's most critical role is moving compute from Earth-bound servers directly to the sensors. This allows our deep space networks to react to data immediately, rather than waiting for instructions to cross the solar system. As we rely more on AI, we face an epistemological challenge. Because we do not have a confirmed signal from another civilization to use as a baseline, we have to train our models on synthetic data. This creates a self-referential risk. An AI might only find the exact signal types we artificially simulated, potentially ignoring true physical novelties. This diagram illustrates distribution shift. The left is clean lab training data. The right is the messy reality of telescope data. External variables, like space weather or new RFI, warp this real-world distribution. If unprepared, the model's accuracy drops. This leads to the black box problem, where an advanced neural network identifies a candidate signal but cannot explain the logic behind its decision. Identifying a potential technosignature is of little value if the scientific community cannot prove the algorithm isn't merely reacting to instrument noise. To address this, astrobiologists are implementing Explainable AI, or XAI. These frameworks allow researchers to peer inside the model's decision-making process. One method uses SHAP values to analyze a radiospectrogram. Instead of a simple detection alert, the model produces a heat map showing which specific data points most influenced the result. This forces the model to expose internal weights. Researchers verify if detection is based on legitimate physical parameters, like frequency drift, rather than artifacts. This transparency provides mathematical proof the detection is rooted in physical reality. We also use blind insertions, where synthetic signals are hidden in raw observational data. If the AI can consistently recover these hidden targets, we know the algorithm is functioning as intended. AI has changed the search for life. It is no longer a matter of waiting for a clear transmission. It is a systematic and validated effort to pull physical evidence from the chaos of cosmic data.